which is being populated during lexical analysis process. Fine. Okay. So in the process, we understood that we should get the attributes from the symbol table. Means sorry, we should attach the attributes for all the grammar symbols in our parse tree, fetch the attribute values from the symbol table, and evaluate the attributes according to the semantic rules. Semantic rules would have been defined when the grammar is formed. So these semantic rules specify how the attribute values has to be evaluated. At the same time, we have seen that we do have two types of attributes. One is synthesized attributes, wherein the attribute value of the parent is computed based on the attribute value of the child. So such sort of evaluation, we call it as synthesized evaluation, or S-attributed definition, S-attributed evaluation. Right? There is another type which we call it as L-attributed, wherein attribute value of a child is either computed from the parent or from the left sibling towards the right sibling. Such sort of evaluation, we call it as L-attributed evaluation. So I told you also that S-attributed evaluation can be pure S-attributed, means we can evaluate all the values of all the parents from their subsequent children's, but L-attributed may not be pure L-attributed, means to say some attribute values are computed from parent to child, some of them may be computed from left to right, and some of them may be computed from child to the parent. Now the question remains is how we can find out which approach to go for. So a rule of thumb is that try to compute the attribute of the parent from the attribute values of child. If the semantic rules do not permit you to do so, then start from parent to child. If that also not possible, do it from left to right. So it all depends on the semantic rules. Yeah. In previous class, we have seen one example of the semantic productions and the semantic rules, and it is a pure S-attributed evaluation which we have seen, and we have constructed the parse tree first for the string 3 into 5 plus 4. We constructed the parse tree. Then we computed the attribute value. That the attribute name is val.val by using the semantic rules, right? So as it is synthesized attribute, all parents' attribute values are computed from child. So digit is computed by digit.lexval, means whatever the value returned by the lexical analyzer. So f.val is computed from digit.lexval. Similarly, t.val is computed from f.val according to the semantic rules. Fine. So finally, we got the e.val, which is computed. And in this entire process, all the attribute values are computed from child to the parent. Means to say, in S-attributed, the attribute value of the parent is dependent on his children. As simple as that. So why I am talking about dependent? So we'll see the dependency and dependency graph bit later. Fine. This is a very simple evaluation, and usually in the question paper question, you're going to have a string byte be given and asked to compute the semantic diagram or SDD, or it might be annotated parse tree for the string. Then step 1 is you should construct you should derive the string from the grammar, means to say you should construct the parse tree. Whether you go for LMD or RMD, that doesn't matter, because our semantic analysis should work for top-down parsers also as well as bottom-up parsers also. So either LMD or RMD. Fine. Once after you have constructed the parse tree, then you should attach the attributes for all the symbols. For example, here you can see E.val, T.val, F.val, like that way. For each of the symbols, whatever the attribute is being given, that is to be attached, and then the evaluation should happen. And usually this is the only question that will be repeatedly asked, called as desk calculator. Right? Desk calculator is the question that will be repeatedly asked. But beside this, we go ahead and see how the L attributed or inherited evaluation is done. Okay. See the grammar. We have some 4 productions here. What is that 4 productions? Number is producing signed list. They both are not together. They are 2 different things. Signed list, 2 symbols there. Okay. Next production, sign is producing plus or minus. List is having 2 productions again. List bit or bit. Okay. 4th production is bit is producing either 0 or 1. This is what is the productions what we do have. Yeah. So now we are supposed to derive the string. Which string? -1 it is a string that is supposed to be derived. How exactly this works? Have a look at this. Number produces signed list. Okay. Now we replace list by bit because we need only one bit, right? So because here we have the production like list produces list bit or bit. So we are taking the bit. Okay. So what is left out is signed bit. What is left out? Okay. So bit is replaced by 1 because bit produces either 0 or 1. And then sign is replaced by minus. So we have got the derivation of this string. So if we construct the parse tree, it looks like this. Number produces signed list, list produces bit, bit produces 1, sign produces minus. Simple. Okay. Similarly, we shall do the derivation for -101. Actually, 101 in the sense it is going to be 5. We are talking about binary numbers, something like this. Okay. Because if we convert 101 into binary, it is going to be into decimal, it is going to be 5. So in this sense, we need to get -5 because there is a minus and 101. So see the thing, number produces signed list. So we are replacing list by not bit, list bit, because we need 3 digits, not 1 digit, right? Again, sign list and bit is replaced by 1. Again, we are replacing list by list bit. So we replace the bit by 0 now. Okay. Again, we are replacing list by bit. Now we get sign and 101. Finally, we get -101. So this is the derivation of the string. See the parse tree. Number produces sign list, list produces list bit. Again, list produces list bit. Finally, the list produces bit. So we are able to derive -101. This is one part of the story. That is, we are able to derive the string. This is as simple as that. We have did it. You have did it many times, even in your earlier semester. Fine. Okay. Now proceeding further. Yeah, these are the attributes. Now the complication is bit increase. Number is one of the symbol which is having the attribute val. Sign is having the attribute neg or negative. This negative may be true or this negative may be false. Negative will be true when there is a minus symbol. Negative will be false when it is a positive number. Fine. But the list and the bit, these 2 grammar symbols, is having 2 attributes. They are not having 1 attribute. They are having 2 attributes. One attribute is position, other attribute is val. So the same for bit also. Bit is also having position and val. And observe, whenever in your grammar or semantic rules you have more than one attribute, then it is going to be an inherited evaluation. Why is it so? Because one of the attribute will be evaluated from top to bottom, that is from parent towards the child or from left sibling to the right sibling. The other one will be evaluated from bottom towards the top, that is from child to parent. We shall see the example. Be careful. This is a bit confusing thing. Please understand carefully. And this is our semantic rules. So what is that? Let's try to understand. Number is having a production, sign list. That's what is the production we have. Then we have now earlier to this in synthesized, for each production we had only one semantic rule. But here we have more than one attribute also, and we have more than one semantic rules also. Then when this production is there, number produces signed list, we have a semantic rule, list dot position. We have two attributes. List is having position and value. List dot position is initialized to 0. That is one of the semantic rules. If sign dot negative, then the number dot val will going to be minus list dot val. If not, if sign is not negative, number dot val is equal to list dot val. So these are the two semantic rules we have. I'm just telling you about the semantic rules. We'll put it into action next. Okay. Sign is having two possibilities, either plus or minus. If sign is plus, sign dot negative is false, else sign dot negative will be true. Okay. List 0 produces list 1 dot bit. I told about 0 and 1. 0 always indicates parent. 1 will going to indicate child. That's what is the thing. So if that is the case, we have three productions here. Three semantic rules here. List 1, that is child's position, is equal to list 0 dot position, that is parent's position plus 1. Means we'll be incrementing the position value for the child depending on its parent. If the parent is having the value 2, child will get the value 3 for the position. Something like that. Okay. Bit dot position is equal to list dot position. Right? Okay. Means to say list's position, parent's position, and the bit's position will be same because it will be at the same level. If you look at it, when the list is producing list and bit will be at the same position. The list again can produce a bit. So for that reason, it is creating a staging there. Fine. Okay. List 0 dot val is equal to, observe now, list 0 dot val means parents list dot val. Parents list dot val is equal to list 1 dot val. That means child's value plus bit dot val. If you can carefully observe this semantic rule, the last semantic rule, parent's value, that is list 0 dot value, is computed by list 1 dot val plus bit dot val. That means from the child's attribute. Parent's attribute value is computed by child's attribute. But if you see the first semantic rule, list 1 dot position, that means child's value, that is position, is depending on or is computed by list 0 dot position plus 1. Means to say parent's position plus 1. Means to say first semantic rule is going in a inherited way. That is position is computed in inherited manner or L attributed manner. But child's means the val, attribute val, is computed from child towards the parent. So two attributes we have for list and bit. Position is one of the attributes which is computed from top to bottom, and the val attribute is computed from child to parents in bottom up manner, means in inherited manner. Right. And then next list can also produce a bit, then also the same thing. Bit dot position is equal to list dot position, and list dot val is equal to bit dot val. Here also position is computed in L attributed manner, and val is computed from S attributed manner. Okay. And bit is having two options. Either it produces 0 or 1. Bit dot val, if it is 0, bit dot val is equal to 0 itself. But if it is 1, bit dot val is equal to 2 to the power of bit dot position. Why is it so? Because when it is 101, if you want to convert it into decimal, we'll multiply the least significant bit, least significant bit into 2 to the power of 0 plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 2. Then only we are able to get the value 5. So as to make that computation happen, we are taking here bit when the bit is 1 there and all, we are computing 2 into bit dot position. So as to make the computation. Fine. I will look at this. We shall put into action and make the things work. Yeah. Here we are computing it for -1, which we have already derived. Okay. Number is producing sign list is producing bit, and that bit is 1 now. and this is minus. Fine. I cannot compute a bit dot val because you can see bit is producing 1. When bit is producing 1, bit dot val is equal to 2 to the power of bit dot position. So as to compute bit dot val, I should know bit dot position, which is not yet been computed. So for that reason, how exactly this works, have a look. First semantic rule to apply is list dot, when list is producing, sorry, number is producing list, signed list, we should make list dot position is equal to 0, right? List dot position is equal to 0, right? Then bit dot position, when list is producing bit dot position is equal to list dot position, right? So for that reason, bit dot position is also equal to 0. Next, what we'll do, we compute the bit dot val now, as we have bit dot position. Bit dot val, bit is producing 1, so for that reason, bit dot val is equal to 2 to the power of bit dot position, that is 2 to the power of 0, that is equal to 1. So from here, we compute back the value because list 0 dot val is dependent on list 1 dot val, means that is a child. So we get list dot val also equal to 1. So from here, as negative is true, for that reason, number dot val is equal to minus list dot val, that is equal to minus 1. So this is simple calculation. We shall make some, means we take a bigger example and we try to solve it. Fine. Okay. Now this is the case. We have this minus 101. We try to compute for this minus 101. Okay. Yeah. Same attributes. Number is having val, sign is having neg. List and bit are having 2 attributes, position and val. Find that. Okay. Now we shall attach the attributes for all of them. Yeah. You can see that bit is having position value. We have just assigned, means attached the attributes, position val, position val, position val, right? And list is having same position and val. We are attaching position and val for list also. We haven't computed the values. Fine. Sign is having negative, that is also attached. So actually, step 1 is you should derive the string from the grammar. Step 2 is you should attach the attributes like this way. Then you should compute the attribute values. This is what is the procedure of constructing the annotated parse tree or obtaining the syntax directed translation, SDT. SDD is specifying attributes. SDT is the translations, what we are trying to do. Okay. Okay, fine. Then a number is having val, that is also attached. Yeah. Now we take up the semantic rule. How to start? I cannot compute the bit dot value or bit dot position, right? Because that depends, means bit dot val cannot be computed because that is dependent on position, and the position of the bit is dependent on list. So for that reason, we obviously need to start with top-down approach. So number produces sign list. For that reason, list dot position of the first list dot position is made equal to 0. Fine. So, and further, when list is producing list bit, list is producing list bit, list 1 dot position, that means child's list position, child list position is equal to parent position plus 1. So for that reason, sorry, when it is producing, list is producing only bit dot position is equal to list dot position. Fine. So for that reason, so list is producing list bit dot position is equal to 0. But now you see this list dot position is equal to 1 because it is plus 1, parent plus 1. Again here it is going to be 1 and this is going to be 2 because parent position is 1. So plus 1 is going to become 2. Similarly, list is producing only bit dot position is equal to list dot position. For that reason, this also becomes 2. See, the attribute derivation is happening from parent to child. But in S attributed, it happened from child towards the parent. Fine. Now we got all the positions of all the lists and bits. Now we need to compute the value, right? We shall do that. The attribute val need to be computed now. Okay. Okay. This point here, I think, right? Yeah. Okay. Now we got positions. From positions, we need to go for val. Okay. The first bit is having the value 1. We shall see that position is equal to 0. Value of the bit is 1. 2 to the power of 0 is equal to 1. Getting the idea? Bit dot val is equal to 2 to the power of bit dot position. 2 to the power of bit dot position. 2 to the power of 0 gave me 1. I didn't got this 1 from this bit value. Bit dot val is computed by bit dot position. Fine. Yeah. Next, here list is producing list bit. Position is equal to 1, but the bit dot val is equal to 0. So because of 2 to the power of because of 0, the val remains 0. Similarly, here 2 to the bit is 1, and here position is 2. 2 to the power of 2 will going to give you 4. So we computed all the bit and list dot positions as well as bit dot val. Now, based on this, we should compute list dot vals. We have computed only bit dot vals. We have supposed to compute list dot vals. We go now from child towards the parent. Observe now, child towards the parent. So because list is producing bit value is 1, and we have computed the most significant bits bit dot val as 4 according to the semantic rules. So immediate its parent list dot val becomes 4, because according to the semantic rule, when list is producing bit, list dot val is equal to bit dot val. Observe the semantic rule. Similarly, you can see here list is producing list bit. For that reason, list 0 dot val is equal to list 1 dot val plus bit dot val. List 1 dot val is 4 plus 0. So because of this, we got a 4 here. Similarly, list is again producing list and bit. We got a 4 on the LHS and we got a 1 on the RHS. So 4 plus 1, we got 5. Finally, negative is equal to true and the list dot val is 5. So we are able to get minus 5. This is attribute evaluation being done. Or this, what you are seeing on the screen, is called by the name annotated parse tree or decorated parse tree. Parse tree is there, which is written in black. The attributes are attached to each of the grammar symbols. One or more attributes are attached, and these attributes are evaluated according to the semantic rules, whatever is being defined, and that is completely shown in a single graph or single picture. This is what we call it as annotated parse tree. You should have parse tree, you should have attributes attached, you should have the attributes evaluated. All these three information together, we call it as annotated parse tree. Just a parse tree, whatever is written in the black. Got the idea? So this much we know. We did L attributed evaluation. The same is true for the S attributed evaluation. The annotated parse tree contains the parse tree attributes as well as the evaluation order. Fine. Okay, now the next thing what we shall do is, chose the decorated parse tree, and also the dependencies of the attributes are shown with the arrows. Fine. Now we have removed the parse tree from the bracket. Got the idea? We have removed the parse tree from the bracket. This is showing only attributes and their evaluation. And usually when we write it or when we do it on paper or board or whatever it is, we are going to give a numbering for each of these arrows. That shows which was the first one to get solved, next one is which one, next one is which one. 1, 2, 3, 4 like this way. We are going to attach a small numbering beside each of these arrows, because that shows which attribute is dependent on which other attribute. And which one is the first to get evaluated and which one is the next to get evaluated. As simple as that. But here we haven't shown in the slide about the numbers. But anyway, removing the parse tree from the back, the rest of the picture, whatever is shown, is called as dependency graph. Why is it called as dependency graph? Because it shows which attribute values are dependent on which attribute values. If it is S attributed, very simple specification that all the parent attributes are dependent on its child attributes. But if it is L attributed, some of them are childs are dependent on the parent, some of them are dependent on the left sibling, some of them are evaluated from child towards the parent. So that order of evaluation is shown in the dependency graph. And remember, for one grammar, for one string, or from one semantic rows, means from the grammar semantic rows for a string, at max we can have only one evaluation. As for a string from a grammar, we must have one parse tree. If we have more than one parse tree, it is a what do you call ambiguity. So we should not have more than one parse tree for a single string. Similarly, we should not have more than one evaluation order for the same string. That's not possible. At most, we must and should have one and only evaluation order. And if that evaluation order is achieved by your syntax semantic analyzer, then your syntactically correct structure is also semantically correct. So you can also think in that way that if you have the ambiguity in the grammar, you obviously will have that ambiguity leading to the more than one evaluation order in semantic analysis also. Fine. Removing the parse tree from the attribute evaluation in the annotated parse tree will going to give us the dependency graph. That's not a formal definition. That's for our understanding. We shall see the formal definition of that. A dependency graph is the directed graph depicts the interdependencies among the inherited and synthesized attributes in the parse tree. This is what we call it as dependency graph. There is an example also being given, which is a synthesized attribute evaluation. E produces E plus E, where E dot val is computed from E1 dot val plus E2 dot val. So this is how the dependency graph has been shown. Okay, and the order in which the semantic rules are evaluated is decided by earlier node to the later node. Earlier node to the later node, either from child to parent or from parent to child, whatever it is. The dependency graph is constructed topologically. Yeah, this and all are some theoretical things that is being told. Grammar is used to construct the parse tree, then obtain the order of evaluation of the semantic rules, and translation of the semantic rules in the order leads to the translation of the input string. So means to say we will have one and only dependency graph for each of the string from the graph. Fine. Okay then. There is an algorithm also being mentioned given in your what do you call textbook also for constructing the dependency graph. Nothing, you construct the parse tree, then attach the attributes, then compute the evaluation order. That gives you the dependency graph, as simple as that. Okay. Next thing is abstract syntax. So I'll tell you, we did construction of parse tree. V is given as an output from our syntax analyzer. That we gave it to the semantic analyzer. It took the attributes and attached the attributes, attributes from the symbol table, attached it, and then it used the semantic rules to compute or evaluate the attributes. And after evaluation of the attributes, we got the annotated parse tree, which is having the parse tree as well as the attribute evaluation together. So if we remove the parse tree from there, we got the dependency graph, which shows the attribute dependency. Then what is this abstract syntax? So this much bulky thing I cannot give it to the next stage of our compiler. Means parse tree, annotated parse tree. I cannot give all these things. Yes, I told you this is a validation phase. If it passes this phase, we are assured that our structure, whatever we have given or whatever the program construct that we have used, is syntactically correct as well as semantically correct. I don't want to carry this stuff further, right? We'll drop it here. We just need to pass it on to the next level. That is our intermediate code generator, code optimizer, whatever it is. Only the meaning of the construct, means the logic of the construct, the mathematics of the construct. That's it. I don't want to carry the programming language details, grammar details, or attribute details, or attribute values. Nothing need to be carried further. So removing all those details, whatever is the pure computation that is remaining, that is sent to the next phase. That's what we call it as an abstract. I can tell you one more thing, that abstract tree is also an intermediary representation. What is intermediary representation? Intermediate representation is that which is free from programming language details, also free from machine language. It is neither oriented towards the programming language, neither oriented towards the machine language. But abstract syntax tree's limitation or is capable of only representing the mathematical expressions. It cannot represent the other programming constructs like loop, or it may be a conditions, or nested things, something like that. Structure or other things cannot be represented. We see what's other sort of intermediate representation we use for them. That's a different part of the thing. Okay. Abstract syntax tree is a condensed form of parse tree useful for representing the language construct of a programming language without programming language details. Okay. Intermediate representation that allows the translation to be decoupled from the parsing details. That's what is the thing. For example, here if I have the grammar S produces if B then S1 else S2, that can be represented like this. For example, here 3 into, the more suitable example is a mathematical expression. 3 into 5 plus 4 can be represented like this. This is not having parse trees, so means to say the grammar symbols, non-terminals, other things. It's just is representing the computation as it is. And if you look at it, all inner nodes are operators, all leaf nodes are operands. As simple as that. We shall see the next example. Yeah, this is giving you the clear difference between the parse tree and abstract syntax tree. The same 3 into 4 plus 5 is derived from the expression, producing expression plus expression, then expression, term, expression, all those things. This entire detail is given in your parse tree, how the string is derived from the grammar. But that is removed, and whatever is the pure leaf nodes, that's what we call it as yield of the tree. Only the yield of the tree is making up our, what do you call, abstract syntax. Fine. So that's what is being mentioned. Fine. Okay. How to construct the abstract syntax tree is as simple as that, no? Similar to translation of the expression into the postfix form. We use subtrees, sub-expressions, and all of this. Leave it, this is not needed. Okay. Means to say, what we are telling is that if I give 3 into 4 plus 5 for you to construct the abstract syntax tree, you can make all the operators as inner nodes, all the operands as leaf nodes, and construct the abstract syntax. As simple as that. Fine. But if at all the semantic analyzer need to do it automatically, then it need to follow some data structure to do that. Correct or not? We should follow some data structure and should have an algorithm to do that. How it does? It does automatically construct the abstract syntax tree by using 3 functions. Understand this. First function name is make node. That function takes operator and will have 2 pointers, left and right pointers. As simple as that. It uses another, it creates an operator node, because your operator should have left node, left link pointing to one of the operand or other operator, and the right link either pointing to one of the operand or other operator. Fine, like that. So this theory looks a bit boring, but when we put it into action, we can see that. We have a leaf, make leaf function for an identifier. which will have ID as well as entry to the symbol table. Similarly, we have make leaf for a number and an entry to the symbol table. Fine. Okay. Now we shall see how it is constructed. Yeah, we are supposed to construct this. For this string, abstract syntax is supposed to be constructed a minus 4 plus c. Okay. So first I call a make leaf with the ID and entry, which will going to create one node with it's a singly linked list, sort of node of a singly linked list, which will going to point to the entry of A present in our symbol table, right? Next we have P2, which is a make leaf. Now it is not an ID, but it's a num, and it is having a value there 4, right? Okay, we are creating make node minus between whom and whom now? Between the node of A and between the node of 4. A minus 4. This much is constructed. And you can observe minus is a doubly linked list. It is having a left pointer as well as a right pointer. Left pointer pointing to our node P1, which is created by make leaf ID, and the right pointer is pointing to P2, which is created by what you call make leaf now, right? So we are giving a names P1, P2, P3 are the names given by us for our understanding or for our reference of the nodes. That's it. You can give A1, A2, A3, whatever it is, so as to give just represent them. Okay. P4 is again an ID node for C. Now it is having entry for C, and then P5 will go into me my node for plus, which is again having left pointer and right pointer. So this is a structure or an algorithmic way for constructing the abstract syntax tree for the given expression. Usually you will get one such variety of a problem for constructing the abstract syntax. If you are given 5 into 4 plus 3 and asked you to construct abstract syntax tree, no, you cannot manually do that. You should formally do it like this way by using the functions make leaf and make node. You cannot deviate that, fine, because this is leading again to one more variety of the problem. Fine? That's the reason. These and all are a simple variety of the problems that you will going to get it in SDD and syntax analysis, semantic analysis, and we have some more to follow which are based on these. Fine. Okay. So one variety of the problem is you may be given test calculator problem for evaluating the attributes of a given expression from child to parent. That is bottom up. Second variety of the problems you may get is the L attributed evaluation. If it is L attributed, sure, they should give the semantic rules, because you cannot guess the semantic rules for the L attributed. They should give the semantic rules, but there is no possibility of giving the semantic rules for S attributed. It is usually the test calculator will be asked. And the next variety of the problem you may get is creating the what you call abstract syntax. There you might be after creating the annotated parse tree, you may be asked to also to write the dependency graph. That is not a big thing. If at all you created an annotated parse tree, the dependency graph can be clearly represented. So this is one of the variety of the problem for constructing abstract syntax tree formally by using make leaf, make node functions. Okay, and there is an semantic rules also for constructing the abstract syntax tree. See that if at all we have E produces E1 plus 3, E will become NPTR, NPTR, and we call make node with plus and one pointer to point to E1, one pointer to point to T. Similarly, we have the semantic rules. This you don't need to remember, just to compensate that how it is going to be procedurally calculated. Right? Okay. There is an example also for the same thing which we have did. Right? Let's see. This is how it is been completed. But don't worry, this is not for any use for us. This is just to justify the concept which we just discussed. Okay. Yeah. The next variety of the graph what we have seen directed acyclic graph. We have seen the dependency graph. We have seen the abstract syntax tree, and we have learned the method of constructing the abstract syntax tree also. Now the next thing what we see is directed acyclic graph. It is also an abstract syntax tree, but with an additional qualification that the directed acyclic graph eliminates common sub-expressions. This is also widely asked variety of the problem. Very simple one. It is an abstract syntax tree with elimination of common sub-expressions. How is it? Just have a look at it. Okay. Identifies the common sub-expressions. It's like a syntax tree. It's also interior node representing the operator and two children's operands left and right. Okay. The only difference is that the node in a DAG representing the common sub-expression has more than one parent in the syntax tree. Means there every instance of a operator and operand will have separate instances, but here the common sub-expressions are eliminated and only one instance is represented. We shall see the example. Yeah, this is what is being asked now. A is equal to B into minus C plus B into minus C. And you observe that B value or C value is not getting changed before or means during this calculation. Means somewhere in between this calculation, B and C value is not changing. Means B or C is not appearing towards your left hand side of the assignment. Correct? So if B value is 4 and C value is 5, B value and C value 4 and 5 itself will be used. Am I correct? Then we shall construct an abstract syntax. It is going to be something like this. Assign is nothing but your equal to A equal to plus B. This U minus means minus of B. That is unary minus. Okay. This is the abstract syntax that has been constructed. Observe now. We have, if at all I read it from the bottom, the yield of the tree, B into minus C, and again B into minus C, two instances, because we have twice B into minus C plus B into minus, and a plus appearing between B into minus C and B into minus C, then that entire value is assigned to A. A is equal to, correct? This is abstract syntax tree, very fair, and we're going to have the doubly linked list for each of the operators. The other things, it is happening. But now we'll see the directed acyclic graph for the same. If at all we see, we have assignment, and observe B into minus C is only one instance, and you can see the same value of B into minus C. Anyway, that 4 into minus 5, whatever the value will come, it's the same, right? 4 into minus C will going to be minus 20. Minus 20 will be the same. The same minus 20 value will be taken on the left hand operator of your plus as well as right hand operator of your plus. Means what's the difference that happens? Observe. If at all we go for that's the common, means the common expression B into minus C is written only once. What's the advantage? What's the difference and what's the advantage of DAG over the abstract syntax? How many nodes I need in the abstract syntax? Let's see. One for B, one for C, right? 1, 2, and one for multiplication. So B into minus C, we need 1, 2, 3 nodes. 3 plus 3, 6, plus 1 for plus 7, plus 1 for A, 8, plus 1 for is equal to 9 nodes we need. But when it comes here, we are reducing 3. We need only 6 in the directed acyclic graph. 1 for B, 1 for C, 1 for multiplication. 1, 2, 3, 4, 5, and 6. A is A, 1 node, like that. So the next part, with what is written there, is called as 3 address code. We shall talk about that later. not right now, immediately. Okay, that's the advantage. When the common sub-expressions are having only one instance, we can reduce the number of leaf nodes and also the number of operator nodes. But anyway, the operator nodes need to be there, but the leaf nodes, eliminating the common sub-expression, we can use the same instance again. Fine. That's the difference between the abstract syntax tree as well as the directed acyclic graph. You can expect one such problem also. Given the same expression, you may be asked to compute abstract syntax tree also, and also the directed acyclic graph. Very bit complicated expressions they are going to give. You should compute them and identify the common sub-expressions and can eliminate them. Right? This is what is the use of abstract syntax tree as well as directed acyclic graph. Three graphs we dealt with. One is dependency graph. After you compute the annotated parse tree, eliminating the parse tree, whatever we get is dependency graph. Next, we computed abstract syntax tree, eliminating all details, representing the expressions, wherein all inner nodes are operators and all the leaf nodes are operands, which is constructed systematically by using make node and make leaf functions. And the last we dealt is directed acyclic graph, which is advanced form of your abstract syntax tree eliminated with common sub-expression. So this completes your semantic analysis, one portion of your what you call module 5. Okay, next we shall go for intermediate code generation. Fine, thank you for joining, and we shall stop here. Okay.